Hello students, welcome back to the physics class. I believe you all listened to the first video, chapter 1, and I'm very pleased and I really appreciate the effort of most of the students who wrote the notes and took a photocopy of it and sent it to me through WhatsApp. I really appreciate you all and I thank you all for your immediate response. Now, before we could start today's class, or before we could get into a new topic, I thought I should introduce the formulas of chapter 1 and then move on to the next chapter. Because problem solving is inevitable when it comes to physics and especially in ICSE. So if your question paper is for 80, at least for 20 or 30 marks you will have problems in it. So make sure that you learn all the formulas in every chapter. Once you learn the formulas, then problem solving would be a very simple thing which you will be able to do very easily. So here we'll move on to the formulas that are involved in chapter 1.
So children, here are the formulas that are involved in chapter 1. So the first formula is tau. What is tau? Tau indicates torque. Tau is equal to F into D, that is force into perpendicular distance. So what would be the unit here? For F, force, the unit is Newton. For distance, the unit is meter. So for tau, the unit will be Newton meter. So the first formula that you will be learning in chapter 1 is tau is equal to F into D, where F is the force and D is the perpendicular distance. And the second we learnt is moment of couple. In the case of moment of couple, there are two torques that are acting on it. What do you mean by torque? Torque is nothing but the turning force. So imagine this to be your steering wheel. With one hand you will be pulling your steering wheel this side, and with the other hand you will be pulling it in the opposite direction. So there are two turning effects acting on a same object. So if I consider this to be the center of the object, the distance between this point and this point, if this would be the anti-clockwise force and this would be the clockwise force. So this is D1 and this is D2. So you have two taus involved. So anti-clockwise tau and a clockwise tau. So tau plus tau. So for this the formula is, again we'll take it from here, force into perpendicular distance, and for clockwise again it is a force into perpendicular distance. Force is common in both the cases, so I can take F outside. So when I take F out, it becomes F into D1 plus D2. So if I add D1 and D2, I will get the exact distance between the two forces. So I take it as a D here. Okay. So moment of couple is F into D, where here it is not the perpendicular distance, it is the distance between the two forces. So again here what would be the unit? It will be Newton meter, because for F it is Newton and for D it is meter. And the third formula we will be learning here is for the principle of moment. I believe you remember this portion which we discussed in the class, and I gave you some examples too. When it comes to principle of moment, for a body to be in equilibrium, the sum of anti-clockwise moment should be equal to the sum of the clockwise moment. Here's a small example. You have a meter scale and you are connecting the meter scale to a thread and you are suspending it at its center, and you are adding a mass this side and to the other side. So we'll call this as W1 and this as W2. What does this weight do? This weight will try to pull the scale towards this direction. So what is this direction? We can call it as a clockwise direction. And what is the work of this weight? This will try to pull our scale towards the anti-clockwise direction. So this I will call it as a clockwise moment, and this I will call it as the anti-clockwise moment. So for a scale to be in equilibrium, this force and this force has to be same. So this will not move to either side and it will stand still. And that's what we call it as equilibrium. Equilibrium is staying at rest no matter how many forces act on it. So here, how do I calculate the moment? Moment is nothing but distance into weight. That's nothing but our tau. Tau was force into distance. So what is weight? Weight is nothing but a force, and L is nothing but a distance. So here L2 into W2 is equal to L1 into W1, which is the sum of the clockwise moment is equal to sum of the anti-clockwise moment. In this case, we have only one weight, W2 for anti-clockwise moment and W1 for clockwise moment. So this formula I will call it as sum of the clockwise moment is equal to anti-clockwise moment. In case if there is another weight acting here, we call it as W4 and another weight here as W3. Now what we will do is we will find the distance like this and we will add that here. So it will become L4 into W4 and here it will become L3 into W3. So this should be equal to this. Then I will say the sum of the anti-clockwise moment is equal to the sum of the clockwise moment. So for this principle of moment, it is nothing but a ratio. So there will not be any unit for it. So these are the three important formulas that are involved in chapter 1. One is torque, second is moment of couple, and the third one is principle of moment in equilibrium.
Make sure that you note down all the formulas. We will be solving problems very soon. So let's move on to the next chapter. Well, we completed chapter 1 and now we are going to move on to chapter 3. We are skipping chapter 2 because it involves a few equations. I think it would be clear when I explain it to you face to face. So what is the name of the third chapter? The name of the chapter is Machines. So in this chapter, we will be learning about simple machines, pulleys, levers, and how it works, what is their mechanical advantage, velocity ratio, and so on. So we'll get into machines. Before we could get into the topic, what does a machine mean? What does the word implies? A machine is an object that makes an work very simple. It makes our work easy. That's it. If you're trying to open a bottle, if you use a bottle opener makes it very easy to open it for us. So bottle opener is a machine. A wheel that we use nowadays is a machine. So whatever you look around, whichever makes our work easy, we can simply call it as a machine. If it's a very simple form, we call it as a simple machine. And of course, computer is a machine, but it's a complex machine. It has so many parts inside it. But here we will be learning about simple machines. Okay, now after knowing what machine is, we will be moving on to the important functions of a simple machine. What does a machine do? Number one, a machine is a force multiplier. What do you mean by multiply? I'm giving you 10 rupees and you multiply into, you use it well and you make it as 40. Then I say that whatever I gave you, you have multiplied it so many times. So you give little and you get back more is what you call it as multiplier. So in the case of a machine, you give a small force, but as a result, you get a higher force. A very simple example is you're sitting inside a car and your car is moving in around 60 or 70 kilometers per hour and you need to stop it. What do? Will you jump out of your car and bring people around and stop it? All you do is simply press the brake that's in your car. So a very small force that you give inside gets multiplied in the process and it helps to stop the huge vehicle. So you give little and you get back more in a machine. So we call machine as a force multiplier. In changing the point of application of effort to a convenient point. For example, you can see the small animation that's going on nearby. All you need to do is make your cycle move. The rear wheel of your cycle is rotated by applying effort on the pedal. You are not giving effort directly to the huge circular wheels that are in your cycle, which makes your cycle move. Instead, we give the effort on the pedal. So you are doing it in a convenient position. If you are asked to give the effort only in the wheel, you won't get a proper position to sit and ride or to balance your bicycle. So you are applying the effort in a convenient position so that your machine works and makes your work simple. Cycle is a machine because it's very difficult to walk a very long distance, but it's quite easy to ride a bicycle. So we call it cycle as a machine. And here is one good example where changing the application of effort point to a convenient position. So wherever you get, no matter where you apply the force, your work definitely happens. So this is a second function of a simple machine. The third important function of a simple machine is changing the direction of effort to a convenient direction. Previous point, changing the application of effort point to a convenient position. That is, you want your work to be done in the wheels of the cycle, whereas you are giving the effort in the pedal. But here in this case, if a bucket full of water is lifted up from a wheel without the use of a pulley, effort has to be applied upwards, right? So if there's a small picture nearby, imagine there is no pulley at all, but you will have to lift the bucket from the well. You will have to apply the effort upwards. But if you are using a pulley, your effort is downwards. And this change in direction of the effort to a convenient direction makes your work very simple with the help of a pulley. You have a machine, and this machine changes the direction of effort to a convenient direction. Here, you are applying the effort in a convenient point. Here, you are changing the direction of the effort to a convenient direction. And a third one, for obtaining a gain in speed. When a pair of scissors is used to cut the cloth, its blade moves longer on the cloth while its handle moves a little. I think you'll be able to understand by seeing this animation. The blue handle could be some 3 inches, whereas the blades will be around 6 or 7 inches. So by moving this 3 inch, you are making this 7 inches to move, which means you are gaining a speed. A gain in speed is obtained in the case of a simple machine. So these are the 4 main functions of a simple machine. What are the 4 main functions? They are good force multipliers. You give a little force and as a result you obtain a larger force. Second, it helps in changing the application of effort point to a convenient point so that it makes your work easy. Third one, changing the direction of effort to a convenient direction to simplify your work. And the last one, it helps in or for obtaining a gain in speed. So these are the 4 important applications of a simple machine. If you listen to it carefully, all the 4 functions of the machine comes inside this definition. I'll read it again. A machine is a device by which we can either overcome a large resistive force. Large resistive forces, for example, let's imagine you bringing up a huge bucket of water out of the well. That bucket is your resistive force, or that bucket is your load, the weight on which you are working. And effort is the force that you apply. Now listen to this definition again. A machine is a device by which we can either overcome a large resistive force, that is a load, at some point by applying a small force at a convenient point and in a desired direction, or by which we can obtain a gain in speed. A machine is something which helps us to overcome the load or overcome the huge object on which we are going to work on. But how? By as a force multiplier, or by changing the application of effort point to a convenient point, or by changing the direction of effort to a convenient point, or by helping in gaining speed. So this is the definition of machine, and this definition of machine involves all 4 functions of the simple machine. Now In order to have a clear understanding of the chapter, there are few technical terms which you should be clear about. So number one, load. What is load? The resistive or opposing force to be overcome by the machine. For example, for example, imagine you're coming to school, you're getting ready, you're well dressed in your uniform, with your shoes on and tie. But before you could come out of the house, there is one thing very important that you carry to school. That's your school bag, which would be really very heavy. And that bag, we can call it as a load, a heavy thing that you have to carry. It's mostly like moving the huge weight from one place to another place. So load is something but a huge object which is quite heavy. Second word that you're going to learn is effort. Effort is the force applied on a machine to overcome the load. So effort is simply the work that you do, the force that you apply. So load is the weight, effort is the force that you apply. Third one is mechanical advantage. The mechanical advantage is the ratio of load to the effort. So it's simply the ratio of load and effort on which you are going to work, the load, and the force that you apply, that's effort. Load by effort is your mechanical advantage. Since it is a ratio, mechanical advantage does not have any unit. And the next one is velocity ratio. Velocity ratio, the ratio of velocity of effort to the velocity of load is called as velocity ratio of a machine. So VE is the velocity of effort, VL is the velocity of load, and VR is the velocity ratio.
Okay, velocity ratio. When I say velocity ratio, let's learn the word. Let's split it into two different words. One is velocity and the other one is ratio. What is velocity? Velocity is nothing but distance by time. It's a very common formula that you know. What's ratio? Ratio is a fraction of something. You have a denominator and a numerator, and that's what you call it as a ratio. Now, here you are having a load and you are applying some effort on it. So we have a load and a effort. So we have two different quantities. Velocity ratio. Ratio should always have two quantities. So what are the velocities that are involved here? Velocity of load and the velocity of effort. As I told you earlier, velocity ratio is equal to velocity of effort by velocity of load. So I can write it as VE by VL. If I write this velocity in terms of distance by time, my formula would become distance moved because of the effort divided by time, d by t, distance by time. Distance moved by the load with respect to time. So I'm not complicating things, I'm just trying to solve it. Velocity, I'm writing it in terms of distance by time and distance by time. So as you know, here this would become like this now. So the t and t would get cancelled, and what will be left out is dE by dL. So the formula for velocity is distance moved by the effort and distance moved by the load. So velocity ratio is equal to dE by dL. We started with velocity ratio is equal to velocity of effort by velocity of load, and we are ending it with VR is equal to dE by dL.
Velocity ratio is also defined as the ratio of displacement of effort to the displacement of load. That is distance moved by the effort and the distance moved by the load. So again, for velocity ratio, we won't have a unit because it is a ratio. If I have to give a unit for distance, and numerator is also distance, denominator is also distance, so it would be meter by meter and it would get cancelled. So it does not have any unit. The next one is work output. The work done by the machine on load is called as work output. And what is work input? the work done on the machine by the effort. So you will have to be very clear in this. Input is work done by the effort on the machine, whereas work output is work done by the machine on the load. So it is the machine that is connecting the effort and the load. So the last technical term that we would be learning now is efficiency. What is efficiency? Efficiency of a machine is the ratio of the work done on load by the machine to the work done on machine by the effort. So in simple, I can say efficiency is equal to work output by work input. And the symbol for efficiency is eta. You can see a small n-leg structure there. It's eta. And again, efficiency also does not have any unit. So if I have to say this efficiency in simple words, I can say that I'm going to teach you, or maybe I'm trying to teach you to draw an apple. I teach you for around 20 to 30 minutes, and then I'm going to ask you all to draw an apple and show me. If your apple is going to be in some rectangular shape or triangular shape, then the effort that I have put in teaching you is of no use, which means the efficiency is very bad. Whereas if you all draw it so beautifully with a leaf and beautifully colored and give it back to me, then the effort that I have put in teaching you to draw an apple didn't go in waste, which means the efficiency is 100%. Whatever I did was of good use to you. So whatever I taught, you have understood and you were able to reproduce it. That's what you call it as an efficiency. You're giving something, if you get it back, then you say that it is an efficient work. If you're doing a business, you're putting an input of 100 rupees, and if you get back only 50 rupees, you call it as loss. If you put 100 and you get back 100, then it's no loss, no gain. If you put 100 and if you get back 200, that is a gain. So a machine is more like that. You're supposed to get at least what you give. If you put in 100 in your business, you should get back at least 100. Then it is a okay, efficient machine. If you're able to get more than 100, then that's even better. So this is what efficiency means. So after learning all these simple, important terms, we are going to learn the principle of a machine. What's the principle of a machine? What do you mean by the word principle? Principle means it has certain rules and regulation or how it works. A principle of a machine. When energy is supplied to a machine by applying an effort, it overcomes the load by doing some useful work on it. For example, if you see the animation here, the person there, he is applying an effort on the load. So effort is the energy that this person is spending, and load is that huge box over there. And what does this machine do? The pulley that's over there on top is your machine. What does it do? It is using this effort to overcome the load by doing some useful work. What work does it do? It lifts the load up. So your effort is being used properly on the load. So this is the principle of a machine. In the case of a machine, your work or input energy and the output energy should be equal. As I told you, in the case of a business, if you put in 100, you should get back 100. So your input energy and output energy has to be equal. If your input energy and output energy are equal, then you call that machine as an ideal machine, which is its efficiency is 100%. You put something inside and you get exactly what you put inside. I gave 100 and I got back 100. I put in some energy and I got the result. Then the efficiency is 100%, and that is what you call it as an ideal machine. When I say ideal, it's always imaginary. You would have learnt about ideal gas. Ideal gas and real gas in the case of chemistry. And you know that ideal gas cannot exist because of course molecules will move and they will have to collide with each other. And so real gas is something that's practically possible. Similarly here, This ideal machine, which has efficiency of 100%, is quietly an imaginary machine. So the actual machines will have efficiency always less than 100%. You can never have an ideal machine. It is quite not possible. I'll tell you why it's not possible. So the actual machines will always have efficiency which is less than 100%. So input energy is not equal to output energy. So I'm giving in 100, but I'm not getting back 100. My input is 100 rupees, but my output is only 80 rupees. Where does that 20 rupees go? Or in terms of physics, I'm applying 10 Newton of force, but my result is only 8 Newton. Where does this 2% go? This 2% goes out, or it goes out as a loss of energy during the operation. Loss of energy, it is getting wasted in some form. What are the forms that are possible is, one is friction. You are using a pulley and you are trying to lift up the load. Of course, there will be some friction that will be acting between the rope and the pulley. So some energy is getting wasted here between the rope and the pulley. The other possible ways by which the energy can get lost are, you are using a string and the string is not perfectly elastic, or the energy can be lost in the form of heat. So these are the possible ways by which your input energy gets transformed into some other energy or as a loss of energy. So input energy is not equal to output energy in the case of an actual machine. But in the case of an ideal machine, input energy is equal to output energy. In the case of an actual machine, efficiency is always less than 100%. But in ideal machine, efficiency is equal to 100%. So this is the principle of a machine.
So we've completed discussing the principle of a machine. Now we are going to move on to relation between efficiency, mechanical advantage and velocity ratio. I believe we learnt about the definition and formulas for efficiency, mechanical advantage and velocity ratio a few minutes earlier, but I'll repeat it again for you. Efficiency, eta, is nothing but the ratio between work output and work input. Mechanical advantage is the ratio between load and effort. Velocity ratio is the ratio between displacement of effort and displacement of load. So we are going to find the relation between efficiency, mechanical advantage and velocity ratio. So before we could move into it, I want you to be clear with what is work. Since we have work output and work input, we'll see what work is. Work is nothing but force into displacement. So what is work input? Work input is effort into displacement of effort. So effort is nothing but a force, and the displacement that happens with respect to effort is what we call it as displacement of effort. So work input is what you do. So that is the effort that you give. So effort into displacement of effort. Whereas work output is your result. The result happens on the load, and this is the displacement of load. So work output and work input. So here efficiency is the ratio between work output and work input. Now we have an individual formula for work output and work input, and we are going to substitute it here. So we know efficiency is equal to work output by work input. What is work output? Work output is nothing but load into displacement of load. Work input is effort into displacement of effort. Now what I'm going to do is, I'm going to divide it into two different multiplications. So load by effort into this load by effort into DL by DE, displacement of load by displacement of effort. What is load by effort? We'll move on here to mechanical advantage. Mechanical advantage is nothing but load by effort. So here load by effort, I can write it as mechanical advantage. And here I have displacement of load by displacement of effort. So we move back to velocity ratio. What's velocity ratio? It is displacement of effort by displacement of load. But what we have is simply the inverse of velocity ratio. So I can write this as 1 by VR, that is inverse of velocity ratio. Now let's apply this here. So what will become? This term becomes mechanical advantage and this term becomes 1 by velocity ratio. So my efficiency is mechanical advantage divided by velocity ratio. So the new formula that we obtain for efficiency is mechanical advantage by velocity ratio. The earlier formula on which we started is efficiency is work output by work input, and now we are landing with efficiency is equal to mechanical advantage by velocity ratio. This I can write it in any way. I can cross multiply and write velocity ratio is equal to mechanical advantage by efficiency, or mechanical advantage is equal to velocity ratio into efficiency. As a conclusion, what I would say is a mechanical advantage of a machine is equal to the product of efficiency and velocity ratio, and I would call this as the relation between mechanical advantage, velocity ratio and efficiency.
So here are some examples for simple machines. Lever, pulley, wheel and axle, screw, wedge, inclined plane, all these are simple examples. Whereas in this chapter, we will be learning about levers and pulley alone. So we'll move on to the next topic, levers. What are levers? Levers are the simplest kind of machine used in our daily life. A lever is a rigid, straight bar which is capable of turning about a fixed axis. As you can see here in the picture, the rod, the blue rod that we have is what we will call it as a lever. For example, imagine a seesaw. Seesaw, the place where you sit, the bar, the wooden bar on which you sit is the lever. And this lever, as I read earlier, is a rigid straight bar. So in your seesaw, the place where you sit is a rigid straight wooden bar, which is capable of turning about a fixed axis. You all can imagine a seesaw. The wooden bar will be stuck or will be fixed to a metal bar that is attached in the ground almost at its center. So, a lever is a rigid straight bar which is capable of turning about a fixed axis. So, it is fixed at a particular point, but it is capable of turning. It's more like a door. The axis about which the lever turns passes through a point of a lever, and it is called as the fulcrum. Or in simple words, I can say that the fixed point is fulcrum. And in one side, you have your load, and on the other side, you apply your effort in order to move the load. So, there are few words which we have to be very clear about when we are learning levers. That are three important words: load, effort, and fulcrum. As I said earlier, fulcrum is a fixed point. Effort is what you do, the work that you do, the force that you apply. And load is the object which you want to move. These levers are classified into three classes: class 1, class 2, and class 3 levers. So, in the case of a class 1 lever, the fulcrum is in the middle, the effort and load are on either side. The effort could be in the right and load could be in the left, or it could be the vice versa. It's simply that fulcrum is in the middle, effort and load are on the either sides. In class 2 lever, load is in the middle, fulcrum and effort are on the two corners. In the case of a class 3 lever, effort is in the middle, fulcrum and load are on the two opposite sides. So if I tell you with examples, you will be able to understand or imagine class 1 and class 2 and class 3 levers. But how to remember this? Which comes in the middle is what you should be concerned about. Let's go from 3 to 1. In 3, effort is in the middle. In 2, load is in the middle. In 1, fulcrum is in the middle. Let's take the first letter of all these three words, E-L-F, elf. I think you're all very familiar with this mythological creature, elf. So 3, 2, 1 is elf. So in 3, effort is in the middle, in 2, load is in the middle, and in 1, fulcrum is in the middle. So this is one important or easy way to remember the structure of class 1, class 2 and class 3 levers. So when you learn levers, load, fulcrum, effort. These are the three words which you should be concerned about. The next important factor is the load arm and the effort arm. So what is load arm? Load arm is the distance between the load and the fulcrum. Effort arm is the distance between the effort and the fulcrum. So it is always the fulcrum. Load to effort is not concerned here. It is only load to fulcrum and effort to fulcrum. So the distance between the fulcrum and the load is your load arm, and the distance between your fulcrum and your effort is your effort arm. So when we are learning about levers, all the important terms are introduced to you. Load arm, effort arm, load, effort, fulcrum, class 1, class 2 and class 3 levers. And I told you what is a lever. Lever is a rigid straight bar which is capable of turning about a fixed axis. Now we are going to learn more in detail about all these three classes of levers. But what are we going to learn about it? One thing we will be discussing more about all the three types of levers or three classes of levers is the mechanical advantage. Earlier, what did we learn for mechanical advantage? The formula for mechanical advantage is load by effort. Whereas here, in the case of a lever or the mechanical advantage of a lever, it is equal to the length of the effort arm divided by the length of the load arm. Your mechanical advantage is more like your efficiency. If your efficiency is 100%, then you call it as an ideal machine. So similarly here, your mechanical advantage has to be at least 1. That is, you put some effort and you get a output. So if your mechanical advantage is greater than 1, you call it as a force multiplier. So to calculate the mechanical advantage of a lever, the formula is length of the effort arm divided by length of the load arm. Effort arm is the distance between the point of application of effort to the fulcrum, whereas load arm is the distance between the load and the fulcrum. Okay, we'll move on to class 1 lever. What is a class 1 lever? Who comes in the middle? Fulcrum comes in the middle. So in the case of a class 1 lever, fulcrum is in the middle, load and effort are on the two corners. So there are many examples which I can give you for a class 1 lever. Seesaw is one good example. Your pliers, your scissors, these are all the examples for class 1 lever. So here, if the fulcrum is closer to the load, what will happen? Like I told you, the position of the fulcrum is not fixed. It could be either towards the effort or it could be towards the load or could be in the middle. As we know, mechanical advantage is equal to effort arm by load arm. Who is supposed to be more? If the effort arm is more, and what will happen if the load arm is more? So the mechanical advantages, for example, simply look at the picture that's given on the side. Consider the effort arm distance is some 2 centimeters and the load arm distance is around 6 centimeters. Let's put it in the formula. Effort arm is 2 centimeter, load arm is 6 centimeter. So if I substitute it here, so in this case it is 2 by 6 and your answer would be 1 by 3 which is equal to 0.333 which is less than 1. Now imagine the fulcrum is near the load. So what happens? Your load arm becomes 2 and your effort arm becomes 6. Now substitute it back in the formula. Mechanical advantage is equal to effort arm by load arm which is equal to 6 by 2. That becomes 3. So your mechanical advantage is greater than 1 when your fulcrum is towards the load. And your mechanical advantage is less than 1 when your fulcrum is towards the effort. So when your mechanical advantage is greater than 1, then you call that as a effective or efficient machine. If a mechanical advantage is less than 1, you don't call it as an efficient machine. So when the fulcrum is close to the effort, more effort is needed to move the load. Whereas when it is close to the load, all you have to do is a small force and your load will move. So that is a force multiplier. When your fulcrum is close to load, your class 1 lever acts as a force multiplier. Whereas when it is near the effort, you have to apply a lot of force and most of the force would get wasted and the effect or the work will be not very efficient. Some examples for class 1 lever are these: hammer, seesaw, hose, pliers, and scissors. We'll move on to class 2 levers. So in the case of a class 2 lever, who comes in the middle? Load comes in the middle. Fulcrum goes to one corner and effort comes to another corner. No matter where you keep your load, your effort arm is always going to be greater than that of your load arm. So here when you are trying to calculate the mechanical advantage is equal to effort arm by load arm. Your effort arm can never be less than a load arm in this arrangement. So your class 2 lever can always act as a force multiplier. The effort arm is always longer than the load arm. So the mechanical advantage is always greater than 1. So this kind of levers can move large loads with a less. Class 2 levers are always force multipliers, whereas class 1 levers can act as a force multiplier and it could be its opposite too. So some examples for class 2 levers: nutcracker, wheelbarrow, car door. You can understand very easily when you look at this picture. Here is what you do. You are applying your effort and your fulcrum and the load is here. The work is being done with the help of a machine on this load. Moving on to class 3 levers. In the case of a class 3 lever, who comes in the middle? Effort, and the corners are occupied by fulcrum and the load. So here, no matter how you change the arrangement, it's always going to be the load arm which is greater than the effort arm. So the mechanical advantage can never be greater than or equal to 1 in the case of the third class lever. The load arm is longer than that of a effort arm. So it is a mechanical disadvantage, or the mechanical advantage is always less than 1 here. But there is one advantage that can happen in the case of class 3 lever is they are capable of increasing the speed. Some examples for third class lever are a broom, a tongs, and the fishing rod. Because why we call it that way? Because see, you have a fulcrum. Fulcrum is the fixed point. Effort is the effort or the force that you apply, and load, with the help of a load some work is being done. So these are the examples of class 3 levers. So I believe you're all clear with class 1, class 2 and class 3 levers. For class 1 lever, the mechanical advantage and velocity ratio can have a value either greater than 1 or less than 1 or equal to 1, depending upon the position of the fulcrum. Whereas for class 2 lever, the mechanical advantage and velocity ratio of class 2 lever are always greater than 1. In the case of a class 3 lever, the mechanical advantage and velocity ratio of class 3 lever are always less than 1. So this is in brief for class 1, class 2 and class 3 levers. So always we act as a good example everywhere in terms of science. So here all these class 1, class 2 and class 3 levers are found in a human body. Class 1 lever in the action of nodding a head. As you can see in the picture, the action of nodding your head In this action, the spine acts as a fulcrum and load L is at the front part while effort E is at its rear part, front and rear, the front and back. Class 2 lever in raising the weight of the body on toe. The weight of the body is raised on toes. The fulcrum F is at the toes at one end. The load L is in the middle and effort T by the muscle is at the other end. And in the case of class 3, raising a load by a forearm. This picture shows the biceps. The elbow joint acts as a fulcrum. The bicep exerts the force E and the load L is on the palm. So here our body acts as class 1, class 2 and class 3 levers. So with this we are coming to the conclusion of section 3A. So one part of the lesson is over. Since you have listened so far, I think you will be able to answer the questions that are coming. So for the previous video, most of you wrote the notes and your notes were very neat and legible. Thank you. And here for this video, you will have to write the notes and you should be able to answer these questions that are here. First, define machine velocity ratio and efficiency. Number 2, name a machine which is used to multiply force, multiply speed, change the direction of force applied. So all these are in the functions of machine. So if you could remember, just write or just get back to the video, listen it again and then answer the question. Third, define the term mechanical advantage, velocity ratio and efficiency as applied to a machine. Derive the relation between the three terms, velocity ratio, mechanical advantage and efficiency. Give 2 reasons why the efficiency of a machine is not 100%. That is why there is no ideal machine. To which class of lever do the following belong? A physical balance, seesaw, an oar of a boat, human arm, pliers, claw hammer, fire tongs, sugar tongs, scissors, wheelbarrow, nutcracker, lemon crusher, and knife. So children, try to find the answer for these questions. Not all the answers are exactly in the video, especially for the last one. You will have to think. Just imagine how a lemon crusher would be, or now imagine how a sugar tongue would be, or how do we row a boat. So try to place the load, fulcrum and effort properly and classify the type of lever they belong to. So with this, we are concluding 3A. Thank you, children. Make sure that you listen the video, understand, and feel free to ask your questions, and I promise to answer your doubts. Thank you.